Hi, and welcome to your class on muscle architecture. So, I'm just going to make this slide big. Here we go. It's being slow. Let's see. Here we go. Okay, so today we're going to talk about muscle architecture. So, we're going to just start off with a little bit of review. There is this link here, which I very much encourage you to check out. And this link here for a song that will be an earworm for the rest of your life. Anyway, hopefully you enjoy that. So just a quick review on the way muscle works is at the biggest level we have the full muscle here. And then the smaller, if we go down one level, we have the fascicle, which is a bundle of muscle fibers surrounded by connective tissue. Then down one level from there is the fibers within that fascicle. And then the myofibrils, so the mini fibers, and then the sarcomeres, which are just these short sections of the myofibril, and that is our contractile part of the muscle. So just as a quick overview, if you remember, we have the myosin and the actin in green here. So the myosin heads cock attached to the actin at the binding sites, and then pull that actin as it contracts, and this causes muscle contraction. So if they keep cycling through this cross bridge cycle, if they keep cross bridging, then the muscle continues to contract. So have a listen to this song and as a review for that. Okay, so now a question for you guys. So how many fibers does a motor unit control? So do you guys remember back to either, I guess, physiology? You probably covered this in. How many fibers does a motor unit control? And the right answer here is really, it depends. So it depends on the muscle. So when we have our muscles that are used for gross movement, gross motor control, say your quad muscles, then one motor unit might control many hundreds of muscle fibers. So remember that it is an on or an off situation. So this is a single motor unit, okay, and it innervates these muscle fibers, so they're all on or they're all off. And so the more motor units you have going to a muscle, the more fine motor control you'll have with that muscle. So for example, our ocular muscles, each motor unit controls very, very few muscle fibers, and that allows for those very, very fine movements of the eye. Okay, so these are the 4 properties of muscle contraction. You need to know these. So we'll go over them one at a time in a minute, but just briefly, they are contraction intensity, the length-tension relationship, the force-velocity relationship, and the muscle physiological cross-sectional area. Okay, so the contraction intensity is the amount of force that a muscle generates. So how much is it contracting? It's pretty straightforward. How can we measure contraction intensity? We can use EMG. So what EMG does is it literally measures the amount of electrical activity in the muscles. Here you can see 2 electrodes, and they're measuring the amount of electricity, the electrical activity going between these 2 electrodes. And you can see here there's 2 bursts on the screen here. In a while we'll actually be doing a lab using EMG, so we'll be measuring the muscle activation using this technology. So have a look around, have a Google, have a look on YouTube, see if you can find some examples of applications for this technology. So just a hint, it is widely used in biomechanics. So the next important concept is the length-tension relationship. So here we have our diagram of the sarcomere again. And when the sarcomere, the myosin and actin are overlapped at the optimal operating length, we call that 100%. And this occurs when, on the biceps, for example, when the elbow is just under 90 degrees. Why under 90 degrees, you might ask? So let's see. So remember how we've talked about where the biceps inserts. So if I just draw a line in there, that's not a very good line, something like that. You'll see that that's where this is about 90 degrees here. So it's 90 degrees muscle. So when the sarcomere is at its optimal operating length of 100%, there's lots and lots of room for the actin and myosin to cross-bridge and for the cross-bridging effect to happen without anything getting in the way. What happens when we increase the length of that sarcomere? So, for example, if you extend your elbow, what you're doing is you're actually lengthening that muscle. And when you lengthen the muscle, the sarcomeres go from this kind of overlap to more like this kind of overlap. So this is an example, it's 170%. So you can see here that it's very, very difficult for that actin and myosin to cross-bridge because there aren't many binding sites available for the myosin heads to bind to the actin. So when the muscle is in its most elongated position like this, no matter how much impulse you're getting to generate force in that muscle, the muscle is very inefficient at cross-bridging at this length. So we can see once we go above 100% of optimum operating length, the amount of force or tension decreases as the muscle gets longer. Similarly, if we shorten the muscle out, so if we flex the elbow all the way, the amount of tension that we can generate also decreases dramatically. And that's because the actin and myosin are actually so overlapped in this position that although there's binding sites available, there's nowhere for it to contract because it's already in its shortest possible position. So just to summarize there, optimal sarcomere overlap is 100%. So in the middle, basically. And this is represented by about the middle of the range of motion of a joint. So it's cross-bridging that affects this force production or tension. Either lower than 100% or greater than 100% affects potential force production, and it decreases that potential force production. I'd encourage you to take a look at this supplementary resource here. This is the Khan Academy, link to the Khan Academy description of the length-tension relationship, and he does a great job at talking about that. The next property of muscle contraction we're going to talk about is the force-velocity relationship. So if you think about it, if you're doing a maximal lift, say a maximal bench press, are you going to do it fast or are you going to do it slow? So I hope your answer is going to be slow. So if you're doing something that's really, really heavy, so a heavy bench press, a heavy squat, if you want to be able to generate as much force as you possibly can in a concentric contraction, then the slower the speed, so the slower you do it, the lower the velocity, the more force you can generate. So here with a very slow velocity, I can generate a lot of force in a concentric contraction. The faster I go, so the higher velocity, the less force I'm able to generate in a concentric contraction. And that's due to the cycling rate. So the cycling rate is that cross-bridging cycle. So the faster the muscle has to cross-bridge, the less force we're actually able to generate in a concentric contraction because there are fewer binding sites activated at any one time because the cycling rate is so fast. In an isometric contraction, velocity is 0, okay? But there is actually some cycling going on in the cross-bridging cycle. If you imagine you can't actually hold your arm out to the side, or you can't actually hold an isometric contraction forever. And if there was no cross-bridging or cycling going on, then we probably would be able to do that, but there's a very slow cycling rate during an isometric contraction. In an eccentric contraction, all of the myosin heads are engaged to the actin binding sites. And what we actually see here is faster velocity, so it's actually faster velocity this direction. Let's see. faster. Oh my goodness. Faster. And then this way is also faster. So if this is zero velocity, fast is going this way and fast is going that way. In an eccentric contraction, we actually see the force that we can produce increase as the velocity increases. And that's due to the elasticity of the sarcomeres. So they have an elastic quality. If it's super fast, eventually they'll actually tear off. Some great resources here. I would recommend you take a look at them. So here is 2 resources by the same guy, and I would recommend taking a look at those. The way I can remember this, so as velocity increases in a concentric contraction, potential force decreases. We can remember that because C for concentric and C for cycling rate. So it's due to the cycling rate that potential force decreases. On the other side of the equation, so with an eccentric contraction, as velocity increases, potential force increases, and that is due to the elasticity. So E for eccentric, E for elastic. So how can we apply this force velocity curve to our training? So here's our force velocity curve, and the red line here is our kind of baseline. Now, if you have an athlete that focuses only on strength, what will happen is you can bend that curve. So they'll actually be able to produce more force, higher force at kind of moderate velocities. But once they go really fast, their force that they can produce really decreases below that average. On the other hand, if you're only speed trained, you lose strength. So you lose the ability to produce as much force, but you can actually maintain a kind of moderate amount of force even at higher speeds, greater velocities. So I think it's pretty clear that we'd want to have some sort of compromise between strength and speed. And this is where your periodized plan comes in. So I know there's a lot of controversy and different opinions on periodization, but a classic periodized plan is designed to ride this force velocity curve, and so you're actually training all parts of that curve so that you have increases evenly, okay? As you gain strength and speed, you're actually going to gain like this rather than some sort of asymmetry there. The final thing we're going to talk about today is the muscle physiological cross-sectional area. So the first thing we need to define is what cross-section is. So if you think about a loaf of bread, okay, here's our loaf of bread. A cross-section is when we cut slices of bread, it's this face of the actual bread, like the part you would butter. That's the cross-section of a loaf of bread. If we apply this analogy to a muscle, and you imagine that the loaf of bread is a muscle, okay, then the cross-section is this kind of cut end of the muscle. If you imagine chopping your bicep in half, okay, then this cut end would be the cross-section. And we can measure that. So, we might measure, the width of this slice of bread would be the width of the cross-section of this bread loaf, or we could calculate the area, okay, of that, and that would be the cross-sectional area of this loaf of bread. Similarly, we can measure the cross-sectional area of a muscle. However, muscle fibers come in different arrangements. So here is a muscle where the fibers are all parallel. And so if we take a cross-section of this, let's do blue, straight across here, okay, we could measure that, we could measure it in the other direction and get an area, and we would get the cross-sectional area. So that was known as the anatomical cross-section. So, oopsie, here we go. The blue would be the anatomical cross-sectional area. So I can mark that on here as well, on this muscle here, and you can see that the fiber arrangement is different. So this is the anatomical cross-sectional area. It's just the muscle straight across, just like our loaf of bread. However, what's different here is the way the muscle fibers are arranged. You see they're arranged diagonally. And so when the muscle contracts, it contracts along those fibers. It doesn't contract necessarily along this anatomical, on this angle here. So if I am going to use yellow here. So the physiological, so that's the physiology of the muscle, the physiological cross-sectional area might be different. So in this case, it's at, ooh, that's a very bad line. I'm going to do that again. No, I'm not. Okay, so there we go. Okay, that's better. So it's at right angles to those muscle fibers would be the PCSA. Please excuse this terrible writing. So you can see that different muscles have different arrangements of the muscle fibers. So the pennation of the muscle is what affects the physiological cross-sectional area. So if we go ahead and draw the physiological cross-sectional area, I'm always going to be at right angles to those muscle fibers. So I could, whoops, that was pretty bad. So I'm going to try and draw it in like that. It's very hard drawing it like this. For this bipennate muscle, you can see it's like almost like a feather. So I'm going to go at right angles. I'm going to try and go at right angles here. So I'll calculate the cross-sectional area of that is a bit more complicated than a unipennate muscle. And then for these multipennate muscles, I'm not going to even attempt to draw it, but it would be like a zigzag arrangement. On Blackboard, you have an activity that looks kind of like this. I would recommend that you print it out. What you're going to do is there's a ruler actually printed on the bottom of that page. I would recommend tearing that ruler off or using a real ruler. And what I want you to go ahead and do is measure both the anatomical cross-sectional area and the physiological cross-sectional area for these muscle diagrams. So I want you to compare this line here with this line here. So which line is the anatomical cross-sectional area? The line of the anatomical cross-section. So that's the one that goes with the anatomy of the muscle, so the overall muscle. So in this example, it would be the blue line going straight across each time. So that means that the green line is the physiological cross-sectional, so the physiology of the muscle. So then go ahead and measure these. So for B and C, you would add this part and this part together to get the full cross-section. And then for C, you would measure this plus this plus this plus this to get that cross-section. So go ahead and write those down on your sheet and compare them. What did you find? So you most probably found that in these muscles with like bipennate or multipennate muscles that the physiological cross-section was longer than the anatomical cross-section. Why is that an advantage? Why do we have muscles that have a larger cross-sectional area? So the answer is that we can fit more muscle fibers into a smaller amount of space. So it makes it quite more efficient that way. We're not going to talk about specifically in this course, but we also have the angle of pennation. So the angle that the muscle fibers attach in depends on how much force they can generate. It affects how much force they can generate. Okay, so just for summary for the whole video, we have the length-tension relationship. Optimal sarcomere length is 100%. However, lengthened or shortened muscles can result in lower tension. Okay, so if you shorten or lengthen those muscles, the sarcomere length is shortened or lengthened. And that affects your force production. It lowers your force production or tension. For the force-velocity relationship, it's different. So for a concentric contraction, as you increase the velocity, you can produce less force, and that's due to the cycling rate of the cross-bridging cycle. However, in an eccentric contraction, as you increase the velocity, you can actually produce a little bit more force due to the myosin heads tearing and the elasticity of the sarcomere. And that's all I have. Thanks so much.